Hello, my name is Satwinder Thiara. My partners are Ryan Salcido and Christopher Sorensen. We are Group 3 and our project is the Flyball Tachometer. We will be covering the background and theory behind the mechanisms involved, the design aspects, actuation of the system, implementation followed by data collection, our calculated results, calibration of the system, the measured results, and a brief look at the bill of materials. So what is a flyball tachometer? A flyball tachometer, also known as a centrifugal governor, is a mechanical device used to measure the rotational speed of a rotating shaft. It consists of a set of weighted flyballs attached to a shaft or spindle. As the shaft rotates, centrifugal force causes the weighted flyballs to move outward, extending the spindle against a calibrated spring. The position of the spindle indicates the rotational speed of the shaft on a graduated scale. This outward motion is proportional to the angular velocity of the mechanism and linear motion along the central rod. Flyball tachometers are commonly used in automotive, industrial, and mechanical applications to monitor and control rotational speeds without using an electrical sensor. In our system, due to the stiffness of the spring, we opted to do without and adjusted our system accordingly.
We designed our flyball tachometer using SolidWorks, with the main structural components being 3D printed with PLA filament. Bearings were fit at all locations where rotating or sliding motions occurred, and the mechanism was powered using a 12-volt direct current motor with a rated speed of 100 RPMs. An ultrasonic sensor was used to operate the displacement of the flyball arms when operating. Shown here is the resting position of the arms and the arms during operation. When not moving, the resting height between the ultrasonic sensor and the flyball arms was measured at 25 millimeters. To calculate the relationship between angular velocity of the motor and motion of the flyball arms, the displacement, or lift of the arms, needed to be measured. Sweeping through different voltages, it was found that at 10.5 volts, the arms would just start to lift off. This voltage was set as the lower operating limit of the mechanism and had an angular velocity of 85 RPMs. Then, the voltage was increased in 1 volt increments until the flyball arms reached their upper operating limit, which was at a voltage of 15.5, an ultrasonic sensor distance of 76 millimeters, and an angular velocity of 140 RPMs. The sensor distance and angular velocity were then plotted against the input voltage to determine if there was a linear relationship. When plotted against input voltage, both the sensor distance and angular velocity were pretty close to linear. After adding a linear trendline and least squares regression fit, the coefficients of determination, or R-squared values, were 0.9821 and 0.9949, which showed that a linear relationship does fit the datasets. Next, a relationship between the ultrasonic sensor distance and angular velocity was created using the previously shown data. A linear trendline was created with a resulting R-squared value of 0.9932. This value shows that the trendline equation accurately follows the collected data. The equation of the trendline was then used in the Arduino code to actively calculate the angular velocity of the flyball mechanism while in operation.
We noted that the main shaft wobbled and caused the circular plate, and therefore the sensor data, to oscillate. To improve the output data stability, the Arduino code was set to average out the sensor data for the past 10 data points and continuously update the average after each sensor reading. The results are tabulated, and the measured motor speed readings are very close to the true motor speed. Sources of error in our system can be attributed to the wobble of the shaft, and we were limited in scope by using a 12-volt motor. In conclusion, we demonstrated that the flyball tachometer could accurately measure the motor's angular speed using the ultrasonic sensor to measure the displacement. We faced issues with the design as the shaft wobbled when operating. In total, we spent about $98, which was within our project's required budget.